So let's go to the next thing. Parthapadim, you want to share the screen and get started?
Yeah. I hope you can see my screen and you can hear me as well.
Yeah.
Okay, thanks. So, hi, my name is Parthapathi Mahapatra. I am a third year PG student at Chennai Mathematical Institute under the supervision of Professor K.G. Arun. First, I would like to thank the organizer for inviting to speak in this symposium. Today, my presentation is about hierarchical binary black hole merger. So, yesterday in the evening talk, you have also listened one talk about hierarchical binary mergers by Vishal Vaibhav. So this work I was doing with my collaborator Anuradha Gupta, Mark Favata, KG Arun, and V.S. Satyaprakash. And this presentation is based on this published article in this astrophysical journal later. So gravitational observations are revolutionizing the field of astronomy and our understanding of compact objects. To date, 90 confident gravitational detections has been reported that are listed in the GWTC3 catalog. The origin of this binary merger is still highly uncertain, with several plausible scenarios that could potentially account for most of the observed events. One single channel cannot explain all the event, while a mixture of channel is preferred over any single channel. Besides that, several high mass black holes are also reported in the GWTC3, with some of them falling in the upper mass gap. And by any standard stellar evolution, you cannot explain black hole in the upper mass gap due to pair instability supernova, and that has led to the speculation of the presence of hierarchical mergers in the LIGO Virgo data. So we have two canonical formation channels to explain the origin of these binary mergers. One is the isolated evolution, and is the dynamical evolution of binary black hole that we have already listened in the Vishal's talk. So I'm not going into the details, but in this cartoon, what is shown is the interplay between different proposed formation channels and hierarchical mergers. So while all the channels can produce first generation black holes, but only some of them that are shown in the orange color that can efficiently assembly hierarchical mergers, and current observation suggests that only some of them can take part in hierarchical merger that are shown in the solid line, but not all of them that are shown in the dashed orange arrows. And one is the necessary condition for hierarchical merger is that the remnant black hole that is formed after the merger that get a kick, and that kick should be less than the escape speed of the environment where the binary is formed. So we know that gravitational wave carries away energy and angular momentum, causing the binary orbit to shrink and eventually to merge. But besides, it also carries away linear momentum and shifting the binary center of mass in opposite direction. So a toy model of gravitational recoil is presented in this cartoon, where in an unequal mass binary, the smaller moves faster than the bigger one, and causing the gravitational radiation beamed in a particular direction, and a net amount of linear momentum is ejected parallel to the motion of the smaller mass, and the center of mass recoil in the opposite direction. Now it turns out that the most of the linear momentum is radiated near the merger, and that's why the numerical utility is one of the best way to tackle the problem of gravitational recoil, and there are already numerical fits available in the literature. So Verma et al. Was first to apply such kind of fits to the gravitational wave data, and they found that the kick posteriors are not more informative, and they are good that to have a precise kick inference, you need to accurate measurement of spin and then of the individual black holes. So in this flow chart, I have summarized different steps of our work. So first we will take parameter distribution samples for mass ratio and spin parameters, because the kick depends on mass ratio and spin parameters for each event from the catalog. And then we will pass through these samples to the inner fitting formula, and we will get posterior of kick magnitude for each event. And that will tell us what is the record escape speed to retain those remnants. And that will help us to infer what kind of star cluster can host hierarchical mergers. So here in these slides, I have shown the probability distribution function and the cumulative distribution function of peak magnitude for few representative events. The left-hand plot show the PDF and the right-hand plot the CDF. And for our work, we use the following Future formula shown in this, developed in these following papers. So you can see in the left-hand plot that the peak magnitudes are not well constrained, not much informative, and we found only one event, that is GW1914, for which we have the well measured peak magnitude, and this is the first reported well constrained peak posterior on gravitational events. And the right hand plot shows the corresponding cumulative distribution function for those probability distribution function for different events. And we'll show in the next slide that cumulative CDF will play a crucial role in inferring the retention fractions of gravitational event in different environments. So let's me explain our inference setup with the example of GW1914. Left-hand side shows the PDF of peak magnitude for this event, and the right-hand side shows the CDF for that event. And if you let's focus on the right-hand plot, CDF, the x-axis is the peak magnitude, while the y-axis the cumulative probability. Now, if you take a particular point on x-axis, let's say 80 km per second, and if you that corresponds to a point of 0.9. So that means that the probability that GW1918 has peak magnitude less than equal to 80 km is 0.9. Now, if this event happens in a cluster with escape speed of 80 km per second, then the retention probability of this event in that cluster will be given by the probability that it has a peak magnitude less than 80 km, and that will be approximately given by this number on the CDF plot. So therefore, the cumulative CDF will be automatically can be mapped to the retention probability versus escape speed plot, which I'm going to show in next slides. So in this figure, I have showed retention probability as a function of escape speed for a few selected events. The x-axis is the escape speed, the y-axis is the retention probability, and the shaded region shows the allowed escape speed range for globular cluster and nuclear star clusters. And these gray curves corresponds to 5 of the 6 events reported by Kimball et al. To be of hierarchical origin. And the red one is, the 6th one is the red one itself, which is 1905-17. This or that, the progenitor of these 6 events may be of hierarchical origin. Now here we are examining if their remnant can participate in further merger and what are the clusters are required for that. So in that sense, our work is complement to their work. So having examined the retention probability for individual events, now I want to extend our analysis to the population, to the entire detected population of GWTC3. So here we'll start with assuming that all the informative detected binary black hole events form a sample retrospective of a binary black hole population in a cluster that will be parameterized by the escape speed. With that assumption, we want to characterize this cluster's stability as a site of future hierarchical growth of black holes through its retention probability. So for a particular escape speed, we can calculate the retention fraction of a particular event used from the reading the data from the CDF. And for a particular escape speed, you can read the data for all the events. And that samples will give me the distribution of the retention probability at that escape speed. And that is exactly shown in these figures. So the distribution of retention probability as a function of escape speed for different star clusters is shown this. The left-hand plot is based on the data from the GWTC2. So when the paper was published, that time GWTC2 data were available, and the right-hand figure is updated with the GWTC3 data. In these figures, the x-axis is the escape speed, the y-axis is the retention probability, and this band show the 90% credible interval, and the solid middle line shows the median of the retention. And if you, in summary, we found that clusters with escape speed of 300 km per second can retain about 56% of the informative population, and cluster with escape speed 80 to 180 km, and that overlaps with the escape speed range of the globular cluster with 180 km at the tail of the escape speed distribution of the global cluster. At that time, median retention probability less equal to 34%. So
Yeah, 2 more minutes, Pradipati.
yeah, some subset of the globular cluster where can entertain hierarchical merger, but overall probability of globular cluster to host hierarchical merger is less, whereas nuclear cluster which have escape speed greater than 200 km per second, they can host hierarchical merger. So these curves don't assume anything about the astrophysical information. So now we want to use the astrophysical information, that is the expected escape distribution of globular cluster and nuclear star cluster, and we want to calculate the retention probability of each events by globular cluster and nuclear star cluster is equation 1. In equation 1, this the PDF of the Higgs magnitude, and Fk is the CDF of the escape speed distribution of globular cluster and nuclear star cluster, and this probability in the square bracket tells me the probability that a Higgs black hole with a Higgs magnitude V Higgs will be retained by a cluster K, and that multiplication with this Higgs PDF integrating over V Higgs will give me the retention probability of jth event in the type of cluster K. With that equation, we have calculated the retention probability of each event for globular cluster and nuclear star cluster, and by bidding this number, we will get the distribution of retention probability, which are shown in these two figures. The y-axis is the number of events, the x-axis is the retention probability. Again, the left-hand plot is the for GW using the data from GWTC2, whereas the right-hand side is the plot using data from GWTC3. And we found that 90% of the event have retention probability between 27 to 41% for nuclear star cluster, and for globular cluster the number is between 2% to 7%. And if you sum up this area of this curve, you'll find the number of events that could be participate in further merger if those happens in a particular type of clusters. And we found that 24 events in the GWTCT could participate in further merger if those events happen in nuclear star cluster, and for global cluster the number is 4 out of 69.
Yeah, Pradipati, please wind up in the next few seconds.
Yeah. So in summary, so we found that to host hierarchical merger, you need a cluster with high escape speed, and that confirms our general belief that globular clusters are unlikely to see hierarchical growth of black holes, whereas nuclear star cluster are the likely hubs for this intriguing phenomenon. So with that, I will stop, and thanks for the attention. I will be happy to take questions.
Okay, thanks, Pradipati. So are there any questions for Pradipati? Okay, Aditya.
Yeah, so I thanks, Parthapratim, for this nice talk. I know we have had this discussion earlier, but so this posterior, so I'm just trying to understand how you get this number of 24 from GWTC 2 or 3. Is this from just the population samples, as in the samples of the population hyperparameters, or is it from each individual posterior?
No, the number I showed here from the population inference, but you can similarly you can get and such kind of numbers from individual events also. But the problem is that when you, I mean, you can give a statement about the population, you should not use the individual events because they suffer selection biases, but you should use the population data. So the number is quoted here using the populations analysis.
Okay, thank you. Yeah, that's what I want to know. Thank you.
Yeah, Kaustav, you want to ask?
Yeah, I have a very quick question. So, what kind of nuclear star cluster or global cluster did you take? By meaning that, did you take a uniform density of the nuclear star cluster? Because what I will imagine is if the merger really takes place closer to other objects, then other than the kick velocity or escape velocity of the host environment, all the interactions will matter, right? So what kind of environment are you really choosing? Are you really choosing a globular cluster with uniform density or just any kind of a globular cluster?
No, we are not. So we characterize the clusters only by its escape speed. So we are not taking any other properties. So here we have not assumed anything about any cluster. We have just taken this is agnostic estimate, just taken the range of escape speed. Now in reproducing this figures, I have used the escape distribution of globular cluster and nucleus cluster, which are available in, using the observed data and which are available in the literature.
Thanks.
Okay, so we are exactly on the 15 minutes. Thank you, Partha Pradeep. And next, you can go ahead.